Chapter 9, Radioactivity. Here are objectives. Describe the alpha, beta, positron, and gamma radiation. Write an equation showing mass numbers and atomic numbers for radioactive decay. Describe the detection and measurement of radiation. Given the half-life of a radioisotope, calculate the amount of radioisotope remaining after one or more half-lives. Describe the use of radioisotopes in medicine. So, Section 9.1, Natural Radioactivity. A radioactive isotope has an unstable nucleus. It is going to emit radiation to become stable. And so when it does, it's going to change the composition of the nucleus. Now, when we're talking about nuclear chemistry, that means we're talking about the nucleus of our atom. Not the electrons that are, taking up most of the space around the outside of the nucleus, but we're talking about the nucleus. So because of that, the particular isotope is identified by the mass number of the isotope. So if we look at magnesium, magnesium's stable isotope is magnesium-24. Notice it has the mass of 24. But it does have some radioactive isotopes that are unstable because their nucleus needs to change the ratio of the neutrons to protons one way or another. And so you will notice here on magnesium-23 that the mass is 23, so we write that as magnesium-23. And on this particular magnesium, you'll notice they still have the proton number of 12, that's why it's magnesium, yet its mass is 27, it's got more neutrons, so we're going to call it magnesium-27. Now, iodine's another example. Stable isotopes, iodine-127 is probably the iodine that, you might be scrubbing to clean different surfaces if you work in any sort of hospital or vet clinic or anything. But there are some radioactive isotopes of iodine that are unstable. And one of the more common ones that's used if you have thyroid issues is they're going to possibly run a test with iodine-131. Notice the mass is 131. It still has 53 protons, just like this particular radioactive isotope, just like this stable isotope of iodine. But it's got more neutrons for our iodine-131. The iodine-125 has less neutrons. And so here's another example with uranium, uranium-235 or uranium-238. Now, nuclear radiation is the radiation emitted by an unstable atom, and so it takes the form of alpha particles, neutrons, beta particles, positrons, or gamma rays. So let's look at these table 9.2 a little bit. This is a good summary. An alpha particle has 2 protons and 2 neutrons. It is quite often written as like that italicized A, which I like that. But sometimes it's written as helium-4-2. And you go, wait a second. So is alpha helium? No, it's not. That's why I don't like it written as 4-2 helium. It is like helium's nucleus, which has a mass of 4 and 2 protons. However, it doesn't have the electrons. So it's not really the atom itself of helium because it doesn't have the electrons. So I'm going to go back for a second. Now notice in this table 9.2 with our alpha particle, here's that alpha symbol. The mass number is 4, just like we said, and it has that +2 charge. Why? Is because it just has the 2 protons and the 2 neutrons. It doesn't have the electrons. It's just a particle without electrons. Now, a beta particle, yes, it's a high energy electron, and you go, wait, you just promised us we're not talking about electrons. We're not talking about electrons outside of the nucleus. But you look back here, what happens, a neutron changes to a proton, and in so doing, you've got to have an electron that's emitted. So in the change, this is what happens. Now you'll notice the charge is a -1, and the mass is nothing. It's 0. That's why they'll also quite often have this E as an electron, because an electron has a mass of 0 and has a charge of a -1. Now, there's opposites. So what's opposite of a beta particle that has no mass and a -1? Oh, well, that's a positron, which has a mass of 0 but a +1. And if we look back at our table, how that is achieved in the nucleus is a proton changes to a neutron and this positron is emitted. So this type of radiation, which has no mass and a charge of +1, is going to be emitted. And it's written like this. Now, gamma rays are the high energy radiation that are released from a nucleus when it decays. Notice, it has no mass, and we don't say that it's changing from a proton to a neutron, or it has any protons or anything like that. It is written as this gamma symbol with 0 mass and 0 for the protons. So, give the name and symbol for the following types of radiation. So see if you can remember that from the last 2 slides. Press pause and come back. So alpha radiation, you can either have the alpha italicized A or helium-42. Radiation with a mass number of 0 and atomic number of a +1, that's our beta positron. That is written as our E for electron, 0, however, it's the positive one. And radiation that represents high energy radiation released from the nucleus, and that's our gamma radiation. All right, so radiation protection requires, if it's just alpha particles, just paper or clothing. That's going to protect you. Unless you're breathing it in. You don't have paper or clothing lining the inside of your body. So alpha particles can be very destructive if you're breathing it in. You go, well, then I just won't breathe it in. Well, one of the things with smoking is that smoking does emit alpha particles. So the alpha particles go right through your lung because there is no inside there, because there is no skin lining the inside of your lungs. All right, now beta particles, it mentions a lab coat or gloves. Maybe you've seen old TV shows or movies where they were kind of making fun of somebody who was trying to protect himself from beta radiation and he was wearing aluminum foil. Well, yeah, that works too. But that's where the aluminum foil comes from, if you've ever seen anything like that. Now, gamma rays, though, it's much harder to stop them, and that's where the lead shield or thick concrete wall, when they thought we were going to be in the Cold War, us and Russia thought that there was going to be, a nuclear war, and there was, of course, all these bomb shelters underground under concrete. Another thing that radiation protection requires is limit the amount of time spent near a radioactive source. If you work in a lab in a hospital that is in the lab where they do a lot of different radioactive procedures, you actually quite often wear a badge that absorbs the amount of energy and that is emitted, and after you've reached X amount of level for that particular week, you aren't allowed to go back in there anymore, which is kind of smart. And last but not least, increasing the distance from the source. Absolutely. Even with beta, you get 10 feet away and you're perfectly fine. So here's a little bit more shielding for radiation protection. You will notice distance, tissue depth, shielding. Okay. So, what type of radiation would be blocked by a lead shield, paper, clothing? Press pause, see if you can remember that. So you notice gamma radiation and our alpha radiation.